Okay, so we're going to do a practice example using some of the time dilation concepts that we talked about earlier. So in this case, we're looking at muons. They are elementary particles with a proper lifetime of 2.2 microseconds, and they are produced with very high speeds in the upper atmosphere when cosmic rays, high-energy particles from space, collide with air molecules. Take the height, L0, of the atmosphere to be 100 kilometers in the reference frame of the Earth, and find the speed that enables the muons to survive the journey to the surface. First, let me just erase some of the notes that I didn't clear from the video we did, which if you haven't seen, then I would recommend checking that out. It was just the previous video. And real quick, I went ahead and said that our proper time, delta T naught, is 2.2 microseconds. L naught is our height, 100 kilometers, and U is the speed that we're looking for. So I think the first thing will be just to write out our equation with time dilation, our equation that we use to find the time dilation. And we're looking for the speed u, so let's do some algebra, right? Multiplying over. I'll go ahead and work through the algebra, even though I'm sure you all could do it. A little bit of algebra isn't bad to do. So we're going to divide on over delta T naught over delta T, or 1 minus u squared over c squared is delta T naught squared over delta T squared. 1 minus delta T naught squared over delta T squared is u squared minus c squared. C squared times 1 minus delta T naught squared over delta T squared is equal to u squared. And speed is c, taking the square root of c squared is just c, times the square root of 1 minus delta T naught squared over delta T squared. Okay, so this is our equation to find our speed, u. It's a little messy, but it's fine. So let's see. C is a constant, we know that. Nothing we're worried about here. Delta T naught, that's the proper time. That was given to us right here. That is our proper time. Oops. So the only thing we really need to find is delta T, which is just going to be our distance over our speed. So I guess it's L naught. The distance these muons are traveling is the 100 kilometers. That's just from the atmosphere down. 100 kilometers times, actually, let's do this. Let's convert it to meters real quick. What was it? Was it 100 or 1,000? It was 100. Let's just do this. Times 3 times 10 to the 8th meters per second. Let's see. 1 kilometer is 1,000 meters. Okay, so let's plug that in. Times 1,000 over 3 times 10 to the 8th. Okay. Ends up being 1 over 3,000ths of a second, or 333 microseconds. Now that we have this, which is just our delta T, that can go right into here. So what I'm going to do is, u is equal to, I'm going to do this bit. Everything inside the radical, I should probably use a different color than red. That's a little silly of me. Purple. So everything that's inside this radical, I'm going to solve for it. I'm just going to keep C as C. It's kind of like how we keep pi, to be exact. It just makes it a little easier sometimes. Delta T naught was in microseconds. That's why we converted that. That was 2.2 squared all over. So I'm just throwing this in my calculator real quick. 333 squared. Okay. So that leaves me with 0.99998 C. So the speed that's necessary is it has to go 99% the speed of light. So that's pretty damn quick. So yeah, the minimum speed that enables the muons to survive. So that's this, 99% the speed of light. And just to recap, we took the equation we got from the last video, and we mostly just algebraically manipulated it till we got to this part. We said, hey, the only thing we don't know is delta t, but that's pretty easy to see. Delta t is just distance over rate. Our rate is the speed of light, and then our distance is L naught. That's how high up it was. And then we just threw all that in. C, I'm just keeping out front. That's kind of common notation. If you multiplied C, you would just get, 2.99 times 10 to the 8th meters per second. But that's kind of standard notation. So our answer is right here. So hopefully that makes sense. Just a little bit of thinking about what the problem's saying. A little bit of algebra. There we go.